Okay. All right, let me go ahead and share my screen. Start the broadcast. Did I get my notification? I don't think I got my notification. Let me get this student. I remember this student. Let's see. Optimize. Let me check something. Figure out what's going on here. I'll be able to go ahead and take its attendance. Oh, guys, trickling in right now. Okay, let me get this last student. So anybody that comes from this point, I'll check attendance again around the 15-minute mark. Let me just log this. It's okay. And then let me just kind of start here for a moment. Give me just a second. Yeah, that's the right account. I might have my notifications on at this point. I'll check it. Cool. Okay, so it looks good. I just needed to confirm that the image was being pushed and everything is working properly. Okay, so let's start here. Let's go to view single page. Okay, we'll start here like that. Okay. All right. So welcome, gentlemen. Let's see. So this is calculus for business, right? That's fine. So let me see, last time I think we talked about limits, right? So section 1.1, and again, limits were really just concerned about how the function behaves when we're close to some x value. Like how do the y values behave as we get closer and closer to some x value on either side? Limits aren't really concerned with how the function behaves at that value. It's concerned with if you go slightly to the left or slightly to the right, you know, is the function approaching the same y value, right? Also, limits kind of push the limits in the sense of we can also talk about when x goes to the far right. So as x goes to infinity or as x goes to negative infinity, how does the function behave, right? So we kind of explored some concepts like that last time. So for today, continuing chapter 1 with differentiation, we're going to take a look at section 1.2, algebraic limits and continuity, right? So here, let's see some objectives here. So we like, and again, I'll check attendance around the 15-minute mark. So in about 10 minutes for anybody that's coming late. Also, as a friendly reminder, the main thing is make sure that you've gained full access to Pearson and you're working on those assignments. That's what everything is basically centered around. I use my YouTube as just like for record keeping. I am live streaming these sessions, so you can always, you know, reference them. I think I've also linked you guys to my sessions of the past, and it's essentially the same content. I tried to make a point to go through each section in detail, in totality. So whatever we don't finish together, I expect you to watch those and use those to fill in whatever we don't do together. So some objectives here. We like to develop and use the limit properties to calculate limits and determine whether a function is continuous at a point, right? So we're going to see what do we mean by those. This didn't display. Okay, I need to go. Oh, okay. Let me see if I can fix this because it's totally not displaying properly. Okay, yeah. It was just throwing a temper tantrum. I had to just exit out and come back in and it was good to go. Okay. So we have these limit properties. Let's do like this so you guys can see. So with this notation, cancel. With notation, a lot of times in mathematics, to me, it feels like it helps if you read the notation properly. It helps to kind of keep things organized, right? So this is read, if the limit as x approaches a of f of x equals L, and the limit as x approaches a of g of x equals m, all right? So the limit as x approaches a of f equals L, the limit as x approaches a of g equals m, and c is any constant, then we have the following. So the first property that we have it says the limit of a constant is the constant, right? So a constant, if you think about that graph is just going to be a flat horizontal line, right, through whatever C is, right? So then as x approaches any number coming from the left or the right, because the graph is a flat horizontal line, it should always approach C, all right? So that's why the limit as x approaches A of a constant is just going to be the constant. Hopefully that makes sense. As usual, if anything is not clear, my recommendation is to unmute yourself to stop me and get my attention. You can also type in the chat. I check the chat periodically as well, but the best thing is just unmute yourself. Hey, unmute yourself and say, hey, Mr. Phifer, can we go back and talk about something real quick? Okay. So another property, the limit of a power function is the limit of the base raised to the power. That is, for any positive integer n, the limit as x approaches a of some function to a power. Let's see. It's almost as if you can pass the limit into the power, right? That's essentially what it is, right? So the limit of the power function is the power of the limit. And essentially, so if you can, one of the properties is if you can pass that limit into the power function like this, we're going to take the power of the limit. Now we've already discussed, you know, this limit is going to be equal to some L. So then ultimately this condenses down into just the power of the limit. Okay. So basically, again, one property is that you can pass the limit into the power function. And then the result is just going to be the power of the limit. Okay. Same thing for the root function. The limit of a root function is going to be the same as the root of the limit, which is going to be the root of the limit. All right. Root of the limit, root of the limit. Okay. Assuming that the limit is not negative when n is even, right? Because you can't take the even root of a negative number. That's all. That's just piggybacking off of things from before. Now this, you know, it might feel one way, but when you start working these, it kind of, a lot of these properties naturally just come out, you know. It becomes second nature the more you kind of work it. The first you just got to kind of, you know, shake off any butterflies and try it. And when you get it a couple of times, these kind of things become second nature, right? So the limit of the sum is going to be the same as the sum of the limits. Okay. The limit of a product is going to be the same as the product of the limits, right? So it's close enough to say that, you know, we're essentially just distributing that function. It's not really multiplication. These are just some properties that hold when we're working with limits. Okay, we got this fifth one. The limit of the quotient is going to be the quotient of the limits, provided that the bottom limit is not 0. Let's see, the limit of a constant times the function is the constant times the limit. So the limit of a constant times the function, essentially you can factor that constant out, and it's going to be the constant times the limit. Okay, hopefully this is okay. All right, let's see if we can see some of these in action. So use the limit properties to find this, right? So one property we said was that the limit of the sum is the sum of the limits, right? So this is going to be the same as, you can essentially distribute that limit into the trinomial, right? So this can be rewritten as the limit as x approaches 4 of x squared. Let's do it like this. Plus the limit as x approaches 4 of negative 3x plus the limit as x approaches 4 of 7, right? So that was just applying one of the properties. I think we also said that the limit of the power is the power of the limit, all right? So for that first one, we can rewrite that one as the limit as x approaches 4 of x quantity squared plus, and you can do something similar. Well, you can like essentially factor out that negative 3. So the limit of a constant times your function is going to be the constant times the limit. So that's the same as negative 3 times the limit as x approaches 4. Again, that's supposed to be a 4 right here. of x, okay? And then we said the limit of the constant is the constant. So that last one is just going to be 7, right? Okay. So then for the first one, the limit of x as x approaches 4 is just going to be 4. Basically, just plugging in 4. So then that's going to become 4 squared. Okay, then it's going to be minus 3 times 4 plus 7. Okay. I think we're okay. 16 minus 12 plus 7. What is that? Negative 5, so 11. So we got a result of 11. Okay. What's the time? I'll give people about 3 more minutes to get in. I'll check attendance at the 15-minute mark. Okay. So using limit properties, we know that the limit as x approaches 4 of x is 4. Okay. By limit property 4, x squared, this is essentially what we did. We got that 16. Okay, negative 3 times 4, I think we got that result. And we got the 7 there. And all together, they gave us the 11 that we got. Okay. So for any rational function f, with a in the domain of f, the limit as x approaches a of f of x is f of a. Okay, so if you have a rational function f where a is in the domain of f, then when you evaluate the limit as x approaches a of that function, you can essentially just evaluate the function at that value. That's essentially what I've been doing. That's what you keep seeing me do, is this property here, right? It kind of becomes second nature, and you start to notice when you have to adjust, right? And so we'll talk about it as it arises, right? I think for this one, we can apply those similar limit properties, or we can just apply what we literally just talked about in the previous slide, and we can essentially just evaluate, I think because the 0 is in the domain of this function, so we can just evaluate this when x is 0. That's going to be what? Square root of 0 squared minus 3 times 0 plus 2. So ultimately, that's going to be what? The square root of 2. And also, again, with anything that you see me writing, you'll get a copy of it. I'll make it available on our box link in Blackboard. Okay. Let me do maybe 1 or 2 more examples, and then I'll check attendance. Okay. So the theorem on limits of rational functions and limit property 2 tells us that we can substitute to find the limit. So the original limit, basically you substitute 0, and we got this result. Okay. We might come back and do this. We're a little bit pressed for time, so I usually leave the quick checks as an exercise for you, just because our time is precious, and I want to try to get through as many like new concepts together as we can. So I'll leave this as an example. It is a good idea to give these a go on your own. Like just give yourself the question and see, can you arrive to those solutions that you saw, right? Try to arrive to those solutions without looking at the answer. Okay. Here we're asked to find this limit. Now notice if we just plug in -3, I think we get 0 over 0, right? So that means that -3 is not in the domain of this function. But I want to say that if we simplify this function first, then we can find the limit. Because again, limit is concerned about what happens when you're close, right? So let's simplify this function first, and then see, can we apply that property where we can just evaluate, okay? So if we were to simplify the limit as x approaches -3, on top, we have x squared minus 9, right? That should be a special factoring technique. Hopefully, you guys are thinking difference of squares, right? So that should give us x minus 3 times x plus 3, right? And on bottom, the x plus 3 persists. Now we have like expressions that can cancel. These cancel. So then that leaves us with the limit as x approaches -3 of x minus 3. Okay. So now we can evaluate this. So then as x gets close to -3, then the function gets close to -6. It's not defined at -3, but when we're close to -3, the y value should be close to -6, right? So then this is going to be -3 minus 3, which is -6. Let's do it like this. Paste. Okay. All right. Let me check this one. Okay. This is just a type explanation of what we just did, and you see the same result. So this means that the limit exists as x approaches -3, but the actual point does not, right? So it's not defined at -3, but but the limit does exist, because when we're close to -3, the y values approach the same number. Okay. Let me pause right here for a moment and let me check for you guys in Zoom. What's that? I see the chat. Let me get these gentlemen. That's an interesting name. I hate to do this. I'm not going to do it because it's really temperamental. There he is. That one. Okay, got that one. No, he's showing up like that. Okay, I see him. Here he is. Okay. And if I check the chat, yeah. So the thing with the waiting room, I do my first wave at the start of class, and I try to get whoever's there, like in that wave, I take their attendance and let them in. I know originally we said that you guys are going to be doing your own attendance, but whatever feature in Blackboard that needs to be set, the administrators haven't set it. And it's just, if I had access, I could just do it myself, but I don't have the access. And they seem like perplexed as to what I'm saying, what I've made it like super clear. But that's neither here nor there. So because I can't get that feature to work right now, I take attendance as I let you guys into the Zoom. Also, I do want to remind you, this is remote asynchronous. You're not obligated to stay. The minimum that I need from you guys on any given day is just to be sure to get into my Zoom so you can get your attendance credit. If you feel flustered or you got, for whatever reason, you're not obligated to stay. Obviously, it's a good idea to stay, just to listen in. You can kind of be chill. With the Zooms, I don't push you guys too hard because this stuff is challenging, right? I do encourage you guys to work together. I know that there was buzz of a group meet last time. It's definitely a good idea to work on this with the tutors. It's a good idea. And just go ahead, and again, all of your homework and quizzes should already be available. You can go ahead and finish all of those assignments for the semester. And that way, the only thing that you'll be waiting on we have 2 exams and a final, right? So you would just be waiting on those. I think exam 1 is during week 6. Exam 2 is like week 14, and then the final, all right? Also, the goal for exam 1 are chapters 1 and 2. The goal for exam 2 are chapters 3 and 4. And then the final, chapters 1 through 4, okay? I think I remember taking his attendance. He just sent me an email. I got the notification, but I think I let him in because I remember his name. But anyway, okay, so example 4. So we're asked to find this limit as x approaches infinity, right? So if we try to plug in infinity directly, obviously it's like, okay, right? But I want to say that we can do a manipulation that will serve us. Let me see. I mean, honestly, you could do that. Okay, so let me go ahead and do what I'm thinking about doing, and if it's not right, we'll adjust. But what I'm seeing is like, okay, let's factor out x squared from all the terms. It shouldn't change the result. It should just change the form into something that we can use, right, for this example. So if we factor out x squared from every term on top and every term on bottom, right? So then this is going to be the limit as x approaches infinity, right? Now on top, if we factor out x squared, let me do this. So we're going to have, I want to factor out 1 in this form. So now on top, that's going to leave us with the first term is going to be 1 plus, if we factor out x squared from the next one, we're going to be left with 4 over x minus 5 over x squared, right? Divided by 2 plus 1 over x plus 1 over x squared, okay? So this is kind of like a trick. A number divided by itself is essentially 1, right? So that term goes to 1. We can even kind of say it goes to 1 like that. So now, when we take the limit, now we let x get really large, right? So now let's focus on this guy right here, right? This 4 over x. As that denominator gets bigger and bigger and bigger, what happens to this circled fraction, right? Because if you think about it, 4 divided by 1 is what? 4. 4 divided by 2 is what? 2. 4 divided by 4 is 16. Sorry, 4 divided by 4 is 1. 4 divided by 8 is a half. 4 divided by 16 is a quarter. Yada, 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 right? So this fraction is doing what? Closer and closer to 0. It's really large, then this term tends to 0. This term tends to 0. Basically, whenever you have some fixed numerator over an infinitely expanded denominator, all of those terms essentially go to 0, right? So that's a trick. That's why we kind of did that first manipulation that we did. And so then now as you let the limit go run to infinity, then the only thing that's going to be left is 1 over 2. Hopefully that made sense. Okay. Again, don't be afraid to ask questions if anything is not clear. So again, my intent is for this time, these are really my office hours. I just fill it with lecture and like homework and stuff like that, just to kind of fill the dead air, just to give you something live. But all the stuff that I'm saying here, they should be in my pre-recorded lectures, right? But the pre-recorded lectures are a little bit better. They go at their own rhythm. They're different. I don't want to say better. They're just different because you can listen to it at two times speed, or you can listen to it at a faster pace. You can always pause, rewind. You can listen, watch it at your leisure. I'm just doing this to just be live and kind of go back and forth. Okay. So let's see, how do we do? First, to divide the numerator and the denominator by the highest power, which is x squared, yada, yada, yada. It looks like they did all the same things that we did, right? And they got the same result of the 1/2. Okay. All right, let's keep going. A quick check again. I leave that as an exercise for you. It's not. Yes.
So when it says limit of x approaches infinity, and when we're solving for the limit, when it says 4 over x, that equals to 0, because it keeps getting closer and closer to 0.
Yeah, as that, because the numerator is fixed, and that denominator, as x goes to infinity, the denominator is getting bigger and bigger and bigger. So that whole fraction is getting closer and closer to 0. So when you go way out to like 10 million, you see what I'm saying? That 4 over x is essentially 0. That -5 over x squared is essentially 0. Does that make sense?
Yes.
And so, yeah, that's the trick when you're like working with infinity, is something of this nature. Okay. All right. That's a good question. Let's keep going. So the quick check, we leave it as an exercise for you, and we have this definition. What's the time? Okay. So we have that a function f is continuous at x equals a if, okay, first we have if f of a exists, that the output at a exists, right? The limit as x approaches a of f of x exists. So the function is defined at a, the limit as x approaches a exists, and the limit as x approaches a is equal to that defined point, then those three stipulations together is what we mean by a function being continuous over an interval from some c to d, right? So again, we're saying that a function is continuous over some open interval, right? Open interval meaning we cannot be equal to the c or the d. It needs to be like a parenthesis or no bar. It has to be that open. It has to be an open interval. But what we mean by function being continuous over an open interval, the function has to be defined at a. The limit as x approaches a has to exist, and that limit as x approaches a has to be equal to the defined function at a. Right? It's three stipulations. Right? So let's see it in action. That's for continuity when x is equal to a over some open interval. So then with this one, we said it asks us, is this function given continuous at x equals 3? So we usually have to have an open interval. Okay, so if we consider the three stipulations, right? The first one is the function defined when x is 3? Okay, so let's do it like let's just do f of 3, right? So if we plug in 3, 9 minus 5 is 4, right? So we're just going to say yes there. Okay. So then for the second stipulation for continuity, does the limit as what x approaches 3 of f of x, does it exist? Okay. Morehouse notifications off. I have to figure that out later. I feel like fooling with that. Let's see. Right. So if we think about this graph, this is going to be a U-shaped curve that we shifted down by 5. Right. So if we think about a parabola that's gone down by 5, so as x approaches 3 from the left or the right, they're going to approach the same y value. There's nothing funky going on there, So we can essentially just evaluate, right? So does the limit exist? Yes, right? It's the same kind of arguments that we had before. And we're going to say yes. And it's equal to, the limit is going to be what? This is the same thing. It's going to be 4. So then the third stipulation, basically we need to show, well, you can just compare those results, but notice that the limit as x approaches 3 of f of x, that's going to be equal to f of 3, right? And then, in this case, it's like 4 equals 4. So then yes, right? The only thing that's kind of irking me, it says it's over some open interval. I guess we could consider over the reals. That should work. But just applying, the 3 conditions for continuity, this is kind of how it goes, right? We evaluate it when x is 3. We show that the limit as x approaches 3 exists, right? And then show that the limit is equal to the value of the function at that point, right? Let's see what happens. Okay. So f of 3 is 4. Wait, let me finish this real quick. F of 3 is 4. By the limit theorem on rational functions, the limit as x approaches 3 of this is also 4. So that's kind of what we've been talking about the whole while. And then since the limit as x approaches 3 is equal to f of 3, then we say that f is continuous at x equals 4, x equals 3. Okay, I know that there was a question. I don't know if it got answered or not.
Yeah, I have a question. So I'm looking at this limit x squared as x approaches 3 minus 5 on number 2. Is it pretty much the same thing as just plugging in x to the function or no?
In this case, yeah. Like that was the first property that we talked about at the start of class. We had these list of properties where we can essentially just plug it in. There will be cases we'll see, they'll pop up where we can't plug it in. Like I think we worked an example earlier when we tried to plug it in, it gave us like the
Yeah.
You see what I'm saying?
Right.
So as long it has some stipulations. As long as it's like a rational function where that a is in the domain of the function, then you can just plug it in.
Okay.
Yeah.
All right. Thank you.
Yeah, that's a good question. And again, you'll start to notice because you'll try to plug it in and it won't work. So then you're gonna have to wait. You're gonna have to like try something different, right? That'll happen. Sorry, it's something on my screen. It's like irking me. Okay, I got it. Kind of. Okay. Oh my god. Okay, it's totally distracting. Okay, anyway. It moved into like a corner and like now it's like fighting, it's like holding on for dear life. Come on. And it's like so tiny, but noticeable. Okay, there we go. Finally. All right, let's see. Let's go on to the next part.
Professor, really quick question.
Go ahead.
So I'm trying to like understand, I guess, each of the rules and like how they differ from one another. That last one was kind of getting.
Oh, number 3.
Yeah. So like for example, we know if they're continuous at 3 different spots. So the first one, I understand that because obviously equal to value. So that's how we know that it is a limit. The second one, is it? I'm not really sure why. The second and third one, honestly, I'm not really sure why that proved it was a limit.
So these are 3 conditions. Like a function has to satisfy these 3 conditions in order to be considered continuous.
Okay.
So it has to, the first numbers 1, 2, and 3 all have to be true for a function to be continuous, right? And so yesterday, we talked about, it was all about limits. So all the stuff we did on limits holds. But remember, when we introduced limits, we were not concerned at the point. We were only concerned when we're close to the point, right? So we saw an example last class where the limit could exist, but the function is not defined at that point. So now what continuity does, it takes the concepts of limit and all it does is fill in that point. Where limits is not concerned with that point, continuity is pretty much the exact same discussion as limit. The only difference is now we're just going to add in that point.
So then if it's like, let's say the point is there, but it's like, it's not equal to up under it, meaning that there's a circle at that point and it's an open circle, not a closed circle. Does that mean it's not continuous?
Yeah.
Okay.
Like if the left-hand limit equals the right-hand limit, it sounds like you're describing a case where the limit could exist, but the function is not defined at that point.
Yeah.
So that's an example of something that's not continuous because it would fail item number 1, where it's not defined at that point. It would fail condition number 1. All right. Let's work a few more examples. I think it's going to become clear. But continuity and limit is the exact same thing. The only difference is for a function to be continuous at that point, it has to be defined at that point. So it has to be defined at the point, the left-hand limit and the right-hand limit, all 3 of those have to be the same. Let's work a few more examples, and I think it'll sink in after a couple of more examples. So is this function continuous when x is -2, right? So we have this piecewise function. We have a piecewise function, and again, all a piecewise function is just multiple functions graphed on the same plane, right? This graph holds when x is to the left or strictly less than -2, and this graph holds when x is greater than or equal to -2. Now we could we can look at the graph and compare, right? And that would help. That would give us a sense. This is just going to be a diagonal line with a y-intercept of 3 and a slope of 1/2. This is going to be a diagonal line with a y-intercept of -1, right? I think they both have positive slopes. So in order for it to be continuous at x equals -2, the first condition is the function has to be defined when x is -2. So let's consider the first condition. All right. So we basically want to evaluate g of -2. Right. And so that's going to be, so if we're going to plug in -2, do we use line 1 or do we use line 2? Right. We're going to use line 2 because it says that's where x is going to be equal to -2. So then that's going to be -2 minus 1, which is -3. That's the first condition. So the function is defined at -2, and the output is basically -3, right? That's the first condition. The second condition is we need to show that the limit as x approaches 2 from the left and the right exists, right? Let's back up. We need to show that the limit as x approaches -2 exists. Last time we said in order for a limit to exist, the left-hand limit has to equal the right-hand limit. Let me do that one more time. The second condition is that we need to show that, I'm going to say need to show that the limit as x approaches -2 of g of x exists. Okay. From last class, to show that the limit exists, we show that the left-hand limit is equal to the right-hand limit. Okay. So as we approach -2 coming from the left, those y values are going to approach some number. As we approach -2 coming from the right, those y values are going to approach some number. If those two numbers are equal, then we say the limit exists and it is that number, right? So as we approach -2 from the left, we're going to use line 1, and then at that point we can just plug in. Okay, hopefully this is okay. Thank you. We're halfway. Let me check attendance again in just a moment. Let me try to wrap this one up and then I'll check attendance again for anybody that's coming late. Okay. So let's look at the limit as x approaches -2 from the left. Okay, so that means we're going to use line 1 of g of x, and this is going to be 1/2 times -2 plus 3. So what is that? 2. Okay, now let's consider the limit as x approaches -2 from the right. Okay, we talked about this superscript, the superscript plus and minus, right? The superscript plus means from the right, superscript minus means from the left, okay? Of g of x. So as we approach -2 from the right, that means we're going to use line 2. So then that's going to be -2 minus 1, which is -3. So does the limit exist, yeah or nay? Right? It should be clear. Does the limit exist? No, come on. Coming from the left, our y values approach -2. Coming from the right, our y values approach -3. So does the limit exist? We would say no. So then, is the function continuous at x equals 2? We're going to say it's not continuous, because condition number 2 fails. Okay. So again, continuity is the exact same thing as limits. All the stuff we said last class, continuity is the exact same thing. The only difference is now you throw in, you got to explore what happens at that point. Limits not concerned at the point, continuity is concerned with at that point, all right? But this is an example where the limit does not exist, so the function is not continuous at that point. Okay, so let's look at the type version. So let's see. I think we got this, right? It is defined. When you plug in -2, you get an output. To find the limit, we look at the left and the right side limits, right? So -2 from the left was 2. As x approaches -2 from the right, the output was -3. Since the left-hand limit is not equal to the right-hand limit, then that means that the actual limit itself does not exist. Therefore, g is not continuous at x equals -2. Okay, I feel like that's a mouthful because this. It's a lot of jargon and lingo, but it's not really that bad. You just need to keep trying and keep pushing, just keep trying, and it'll sink in. But again, the main thing for limits is that it's concerned with what happens when you're close to the point. Continuity is the exact same thing, but now just it's concerned. Not only is it concerned with close to, but it's also concerned with the value at a point, okay? And so it has to satisfy those 3 conditions in order to be continuous at a point, okay? So the quick check I usually leave as an exercise for you guys, okay? We might come back. Let me see the time. We got a good amount of time. Let's keep going. Okay, let me see. So we got to the end of this section. So what I'd like to do is, with the remaining time for today, let's try to go through some homework, at least for section 1, 2, and or section 1, 1, right? So let me take a moment to log into Pearson. Let's see. Let me just close all these. Okay, let's go to Pearson. Come on. Allow. And I am working on an iPad, so this does work with iOS. It is, if it gives you trouble on iOS, you have to allow cookies for Pearson, and you have to allow pop-ups in order for it to work. Allow. Come on. Let me just reload it. Allow. There it is. Okay. So this is this course, 6 with unpaid temporary access. So that's okay. Do what you got to do. Allow. So once you get logged into Pearson, it should look something like this. Okay. Send this thing up. So let's work on section 1.2. All right. I know we're a little bit behind. We just have to do the best that we can. Okay. And essentially we'll be doing one section a day until we get caught up. And I think we can do it. It might be due, but you can go ahead and watch those lectures on my pre-recorded lectures. I'm just doing this to just try to do my best to kind of touch on each section, at least one section a day. Simplify by removing factors. Actually, this is a review. Let me skip this one. I want to get into 1.2. Okay, let's start here. So we're asked to classify the statement as either true or false. Come on. Let's see. So the limit as x approaches 3 of 8 is 3, right? I think one of the properties we said was that the limit of a constant is the constant itself. So this limit should be 8. So when x is 3, the output is always 8, right? So is this true or false? This should be false. Okay. So find the given limit. So this is an example of something, it's a rational function, right? So where the -4 is in the domain of the rational function, so you can essentially just substitute and solve, right? Let me, come on. Yeah, I want this off. Okay. So I'm going to take some notes here. If we plug in -4, that's going to give us negative parentheses. It's going to be -4 quantity squared. I'm just taking notes for right now. Plus 3 times -4 minus 4, right? That's all we're really going to do here. So then -4 squared is going to be 16 times a negative is going to give us -16. 3 times -4 is -12 minus 4. So -32. I was just taking notes. So then I'm gonna get rid of my notes and just submit the result. Okay, let's go with that. Okay, let's go to the next one. I use the theorem on limits of rational functions to find the limit. If necessary, state that the limit does not exist, all right? So notice that the -6 is not in the domain of this guy, so we need to simplify it. I think we did an example like this a moment ago. It's the same thing, just with different numbers, because the top is difference of squares. So that factors into x minus 6 times x plus 6. So that leaves us with x minus 6, right? And then when we plug in -6, the output looks like it's -12. Okay, I like that. They fixed that. Okay. So use the limit properties to find the following limit if it exists. So now, if we tried to let x run to infinity as is, then it's not really going to make any sense, all right? But if we use that trick that we used during lecture like a few minutes ago, then maybe it'll put it in a form where we can let x get really large, right? So if we factor out x on top, we're going to be left with what? 2 plus 7 over x. All right? If we use a similar technique. And then on bottom, we're going to be left with 7 minus 2 over x. So now, as we let x get really large, or we let x run to infinity, those second set of terms tend to 0, and we're going to be left with 2 over 7. All right? Just 2 over 7. Let me get rid of all this other stuff. All right? Okay, let's go with that. Let me see. 2 over 7. You factor out x. Yeah, that's gone. That goes to 0. That goes to 0. What am I missing? Oh, okay. Type an integer or a decimal round to the nearest thousands. Okay. Hey, Siri, what's 2 divided by 7?
2 divided by 7 is approximately 0.2857.
2857. It says rounded to the nearest thousands, tenths, hundred thousands. So that's 3 decimal places. So that needs to be a 6. So we just had the wrong notation. We had the right application of the concept. We just didn't follow directions. Right? Okay. So find the indicated limit. A moment ago, we said that the limit of the quotient, the limit of the root is the same as the root of the limit. So essentially, as long as 1 is in the domain of the function, we can pass it through. So it's just going to be 8 minus 4 is 4. Square root of 4 is 2. So that should just be 2. I just plugged it in really because 1 is in the domain of the function. Okay, and based on the properties that we said a moment ago. What's the time? Determine whether the function shown is continuous over the interval from -6 to 6. No, right? Because I think this is an example of, we have that hole or a gap, right? When x is 4, there's a gap. So is it continuous? We're going to say no. Plus, we also have that region where the limit, smooth, continuous, that sharp corner, it's hard to talk about the limit, as x approaches -2, but you can use either one to say that the mainly the open circle is why the function is not continuous. Okay. Use the graph to find the following limits. So for part A, the limit as x approaches 1 from the left. So 1 from the left, the y values are approaching 4. Okay. So 1 from the left, we're going to say 4. Okay. For part B, as x approaches 1 from the right, the y values are approaching 0. Okay. But then for C, so the limit does not exist because the left-hand limit does not equal the right-hand limit, right? Coming from the left, y is approaching 4. Coming from the right, y is approaching 0. So because those two limits are different, we say this limit does not exist. Okay. And then when x is 1, the corresponding y value is 4. All right. So this would be an example of something that's not continuous when x is 1 because the limit does not exist. Okay. Let's see the time. We got a solid 25 minutes. We might even be able to get through section 1.1 because we are breezing through this. So use the graph to answer these questions. Find the limit as x approaches 4 from the left and the right, yada, yada, yada. Okay. So the limit as x approaches 4 coming from the right. Let's go back. Where is it? We can't see. Okay, 10. Okay, I see it now. So as x approaches 4, 1, 2, 3, 4, coming from the right, our y values are 1, 2, 3, 4, 5, it looks like. So as this function approaches 4 coming from the right-hand side, y values are approaching 5. Okay, so I'm gonna put 5. Wait a minute. Okay, so then the limit as x approaches 4 from the left. So as x approaches 4 coming from the left, the y values looks like they're approaching 1. So I'm going to put 1. So then, because the left-hand limit does not equal the right-hand limit, then we say that the limit does not exist. Okay. Is f continuous at x equals 4? We're going to say no. C. Oh, f of 4. Okay, sorry. So for part C, it wants us to evaluate when x is 4. The closed circle is at 5. So f of 4 is 5. Okay. And then for D, is the function continuous at 4? We're going to say no. It's not undefined because the limit does not exist, right? So it's part B. And again, just stop me if anything is not clear. Let me check on you guys. See, we still got a pretty good house. You guys are doing good. Let me get these gentlemen. So if I hop here, there's that one. And see, who's the other student? Oh. Hang on. Ethan. So it is important that you guys show your last name so I can find you. It's like I just let a student in, but I don't know what his last name is. Mr. Ethan, are you there? Mr. Ethan, are you there? There he is. Yeah, so, you know, it's a good idea. Just go ahead and make your Zoom name so that it has your last name, so that way I'm not wasting time looking for you. Let's keep going. Did somebody have a question? I know somebody had unmuted themselves. Do you have a question or? Okay. Let me see the time. Oh. Okay. So is this function continuous when x is 2? Why or why not, right? So again, 3 stipulations for a function to be continuous at a value. 1, the function has to be defined at that value. 2, the limit has to exist. And then 3, the limit has to be equal to the function at that value, all right? Okay. So let's see. First is this function defined when x is 2? So when x is 2, the output is going to be 2, right? So it is defined because basically we're going to use line 1 because that's when x is going to be equal to 2. Condition number 2, does the limit exist when x is 2? So coming from the left of 2, the limit is going to be 2. Coming from the right side of 2, it looks like it's also 2 because it's 4 minus 2 is 2, right? So the left-hand limit equals the right-hand limit. So we say, yes, the limit exists and the limit is 2. Again, because the left-hand limit equals the right-hand limit, okay? So because the function is defined at 2, which is equal to 2, and the limit exists, which is also equal to 2, because condition number 1 is equal to condition number 2, that's the third condition. So then we say, yes, this function is continuous at x equals 2. If you were to look at this graph, these 2 diagonal lines should connect. They should connect, right? Let's see. We're going to say the function is continuous because f of 2 equals the limit as x approaches 2, and they're both equal to 2, right? They're both equal to the same number, right? So we're going to go with D. Okay. And again, just if anything isn't clear, if I need to slow down or go back, feel free to unmute yourself to get my attention. Is this function continuous?
I have a question real quick.
Yes.
Yeah, real quick. Sorry. This is more like just the classwork stuff. I'm looking in it now. It's quiz week 2's quiz. It's due on the 29th. Correct.
Should be this upcoming Sunday. Week 1 and week 2, I made them do this upcoming Sunday.
All right, great. Thank you.
Yeah. So I want to say each assignment has its due date next to it. Also, as a friendly reminder, even though each assignment has a due date next to it, you can work on any assignment past the due date with only a 10% late penalty. We get unlimited attempts at all assignments, including exams. And the system is set to take your highest score. So even if you're late, the highest you can earn is a 90 on any assignment, but you know, that's still not bad. You can still earn an A all the way up until May 12th, right? Okay. But it gets harder when things are late because it has to be a perfect score to get 90%, which is like an A minus, all right? Okay. We got a solid, I don't want to keep you past 7:10. So we got a little, just under 15 minutes. Is this function continuous over the open interval -8 to 8? Why or why not? Okay. So this is a rational function. -9 is the only real number not in the domain of this, right? It should be defined for all reals except -9. Notice that -9 is not inside this open interval. So then we would say that this rational function is continuous over this open interval because the -9, the only thing in question is outside of this open interval, right? Our claim is that it's B. Yes, the function is continuous over this interval because G is a rational function and the values over this interval are in the domain of G. Does that make sense? Right? So again, I think earlier today we said a rational function is continuous. Well, actually, no. What I'm trying to say is not what we experience. I said it a moment ago. And now it's like I feel like what I'm trying to say doesn't feel right. But in this example, the open interval was restricted to -8 to 8, right? So you have to ask yourself, is the function defined over this open interval from -8 to 8, right? When you look at this rational function, the only number that we have to throw out is -9. Notice that -9 is outside of this open interval. So then that means that this rational function should be defined or continuous for all x's in this open interval, right? Okay, now if they had said something like -10 to 8, then it would be a different story, all right? But we're gonna go with this one, okay.
Wait, Professor, can you explain the thought process behind that one more time?
Okay, let me pull up, because there was something from the notes that I'm actually trying to reference and I'm just not seeing it the best. Let me see if I can find it. It was something, it was like a definition. It was kind of towards the beginning as well. Limit property, not the properties, not those. This is when we started talking about continuity. Give me just a second, right? Was that it, the theorem? No. The limit of this, what is that? For any rational function with A in the domain, right here, right? So this slide right here, this is what I was trying to say. Limits of rational functions for any rational function. And I think the trouble was I kept wanting to say continuous, and I was like, no, it's not. That wasn't a discussion about continuity. I was interchanging limits with continuity. That's where I was getting mixed up, right? Because for continuity, we got to satisfy those 3 conditions. So that's when I knew. I was like, well, what I was trying to say wasn't right. This is what I was trying to say. For any rational function f with A in the domain of f, the limit as x approaches A of that function, you can basically just evaluate it, right? So you can evaluate the limit as long as, if that A is in the domain of the function, you can just evaluate. That's what I was really trying to get at. So for that previous one, the only this function is going to be, the limit is going to exist everywhere except at when x is -9 in this case, because -9 is not in the domain of this function. So the only x value in question here was -9, and notice that -9 is outside of this open interval. So because the -9 was outside of this open interval, then we were Gucci. We were good for these points inside. You could also click on get more help and view an example. And to view an example, what it'll do, it'll just give you the backstory and it'll give you an explanation, all right? So this function is a rational function. Since G is a rational function, the limit as x approaches A is going to be equal to G of A for all values in the domain, right? All values of A in the domain of G. So the only one that they had to throw out in their case was -3. Notice that -3 is not in the given open interval. right? Okay. So, I mean, it's still kind of along the same lines like what I said, but, you know. And then it's like, also, this is why I encourage you guys to work together and work with the tutors, because I may or may not say something that resonates, and you kind of got to keep looking at it or keep getting different perspectives until it clicks. If I'm not saying it a way where it clicks, your class might be like, oh, well, you know what? He's totally overcomplicating that. If you just think about it like this, you know, that might work. Or the tutor might say something along those lines. So that's why it's like I encourage you guys to like work together and like try to get as many perspectives until it clicks. Let me see, how many more? We got a few more. Let's give this one a go. It says the candy factory sells candy by the pound, charging $1.60 per pound for quantities up to and including 35 pounds. Above 35 pounds, it charges $1.50 per pound for the entire quantity, plus a quantity surcharge of K. If X represents the number of pounds, the price function is shown by below. So we have this piecewise function. Find the K such that the price function P is continuous at X equals 35, right? So in order for this to be continuous, we have to satisfy those three conditions, right? The first condition is the function has to be defined at that value of A. In this case, A being 35, right? So I think it's already defined, right? Because if we use line 1, we plug in 35, we're going to get a real number. So we're good to go there. The second condition is that the limit has to exist. The limit as X approaches 35 in this case has to exist. In other words, the left-hand limit has to equal the right-hand limit, right? So as we approach 35 coming from the left, we're going to use line 1 and we're going to get an answer. Then as we calculate the limit as X approaches 35 coming from the right, we need to get the same answer. All right, let's do that one more time. In order for the limit to exist, as X approaches 35 from the left, we get an answer from line 1. As X approaches 35 coming from the right, we need the answer from line 2 to be the same. So we just set up an equation to solve. Okay, let's give it a go. So for instance, if we plug in 35 into line 1, hey Siri, what's 1.6 times 35?
That would be 56.
Okay, so when we plug in, as we approach 35 coming from the left, from line 1, we get an output of 56, right? So then basically what it is, when we plug 35 into line 2, we need it to equal 56. So we're gonna make an equation. It's gonna be 1.5 times 35 plus K, that needs to equal 56. Now we have one equation, one unknown we can solve. Hopefully that was okay, okay? So I'm just gonna use my calculator. Hey Siri, what's 56 minus 1.5 times 35?
56 minus 1.5 times 35 is 3.5.
3.5. So it sounds like K needs to equal 3.5. Type in integer or a decimal. We're gonna cross our fingers, right? Okay. If I need to run through that one more time, I can. I don't know if that's gonna help or not because I'm kind of gonna say the same thing. If I need to recap that, okay, I'm gonna go forward. Okay, was that it? No, oh, that was it. Okay, I know we skipped some in the beginning. I'm gonna leave those be. We got a solid 5 minutes. So I want to just take a few minutes to, I want to go through a few questions from 1.1, if I can get this to open in time. But I don't want to keep you past 7:10. I know class runs at 7:15. I usually use like the last 5 minutes for like Q&A or whatever, or just whatever. If this opens, it's kind of throwing a tantrum. Oh, come on. Okay. Allow. Okay, so let's take a moment and just touch on a few questions from 1.1. We got through the bulk of 1.2. It looks like we jumped around. Let me start with question 5. Okay. So this comes from section 1.1, question 29 from the back of that section. Okay. It says, decide from the graph whether a limit exists. If a limit exists, find the value. So does the limit exist as x approaches 5? So as x approaches 5 coming from the right, the y values are also approaching 3. So we're going to say A, the limit is the real number 3, right? Because the left hand limit equals the right hand limit. Okay, even though it's not defined when x was 3. As x approaches -2, so -2 is on the left hand side. So as x approaches -2 from the left, y approaches 1. As x approaches -2 from the right, y approaches 1. Kind of using that vertical wall method. And so they're hitting the vertical wall at the same point. So then the limit as x approaches -2 is going to be 1. Because the left-hand limit equals the right-hand limit. And they both were equal to 1. Okay. The limit as x approaches 4. This one looks funky, right? The y values, okay. So as x approaches 4 coming from the left, the y gets closer to 0. As x approaches 4 coming from the right, y still gets closer to 0. So it looks like the limit is 0. Because as you come from the left or the right, both the y values look like they're both approaching 0. I guess we got that wrong. Use the graph to find the limit. Is it vertical? 4. What am I missing here? Is it not 0? You know what? It's not 0. It's like it's a perfect fraction. Do we need to calculate this one? Let's see. I'm going to actually do the viewing example. See what they say there. It might be some more to it. So this one, as x approaches -4. Oh, let me see. Oh, I see what I was doing wrong. I was looking at the wrong thing. Okay, I see it now. It's like up there. That's like 2.5. Let me see if I look at hours. No, let me finish that example and see what they say. So it says as x approaches A, the limit of f blah 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 from the left to right exists. If the limit from the right does not equal the limit from the left, it doesn't exist. That's fine. Okay, yeah, we get that. To the left of -4, okay. Oh, is there an asymptote there? No. Oh, -4. Yeah, theirs is on the asymptote. Am I looking at this wrong? Oh, okay, Daruru. I don't know what I'm thinking. Yeah, right? Okay. I guess I was just ignoring it. I wasn't like paying attention, right? So at 4, we have a vertical asymptote. I don't know why I was not seeing this asymptote, right? So at 4 here, at 4, we have an asymptote. So as we approach 4 coming from the left, y tends to positive infinity. As we approach 4 coming from the right, y tends to negative infinity. I don't know why I was like just adamant about ignoring that thing, right? So with that, we're gonna say the limit does not exist. We have an asymptote when x is 4. I don't know, I think I'm just like not here. Let's try another one. Let's do one more and we'll call it a day. I see the time. Thank you. Stop. Let's see, graph the given function and find the specified limits. If necessary, state that it does not exist, okay? So this graph is x squared minus 8. That's gonna be a U-shaped curve that's been shifted down 8 units, right? So the only one that's been a U-shaped curve that's been shifted down is A, so I'm gonna go with A. Okay. The limit is x approaches 3, right? 3 is in the domain. So 9 minus 8 is 1. So I'm just gonna go with 1. All right, because I don't think there are any restrictions on this one. And then the limit is x approaches 1. Again, no restrictions. So I'm just going to plug in 1. 1 minus 8 is -7. So I'm just going to go with -7. I was totally ignoring it. I'm so mad at myself. I was ignoring that asymptote. Anyway, okay. So that is essentially time, you know. Let me go ahead and share these notes because I know I started on homework. I don't think I wrote anything for the homework copy of the notes that we did today. Not college algebra. Come on. I get it. So we're not going to work now because of that. Let's send this to box. There we go. Come on. Come on. All right, it's still throwing a tantrum. Let's see. Do I need to like log in the box or something? Okay, there it is. Spring. Are you gonna do this for every folder? Thank you. This is calculus for business. Notes. Handwritten notes. And we're gonna put it here. It's in the box, okay. So when this bar finishes loading, you'll get a copy of anything that you saw me writing regarding the notes for today. And if there aren't any burning questions, we're gonna go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your evening, guys, okay? Take care. I'll see you Monday, same time, same place. Enjoy your weekend. Take care. Peace. Okay, let's check Zoom.